Okay, hello everyone. It's Mugisa Joseph presenting to you lendshied AI and explainable your model ensemble architecture for microfinance credit scoring under severe class imbalance and institutional domain shift. Yeah, just my timing. So these are the contents that we shall be discussing throughout this session. And then going straight from to the background, what the issue is actually. So the issue is that Tier 4 institution, finance institutions in Uganda, that comprises of over 2,000 SACCOs and microfinances and manages approximately 3 trillion Ugandan shillings annually. Mm, Despite of these values, these institutions operate outside the formal credit bureaus. They lack also formal credit histories, and then have no ability to carry out data-driven decisions. Loan grant decisions are just based on relationships, not data, and then also maybe some kind of repayment narratives that loan officers can have. All this results into high portfolio at risk of about 15 to 25%. Compared to the 5% global benchmark reported by the World Bank. Um, it's a bad one. So up to 25, let's say the implication of 15 to 25% per is that for every 100,000 that is given out, about 25,000 may never return, and that's a very bad amount. These figures, statistics reported as per Bank of Uganda, and then these are some of the terms that we are going to meet there. Module 1, which is our application gatekeeper, which scores loan applications before loans are disbursed. And then module 2 is the loan monitor, which gives us the predictions, like classifies the running loans as maybe stable, elevated, critical. So stable is a normal loan, elevated is in the middle there, critical loans are like those loans which you have to take serious, do some actions, but the model will be able to suggest the actions for you to do. Then this is the model that managed to be our experiments produced as the best model for this kind of the problems that we have. Then SHARP is a mechanism we are using to explain every kind of prediction that our model makes. So because that is necessary by the regulations. And then related work, we have AI in banking, which uses logistic regression. It's a linear model, so which fails terrible on nonlinear circle interactions, the data that exists within the microfinance institutions and circles of Uganda, they are nonlinear. So this model fails terribly. So, and then we also have effective predictive prediction, which uses random forest but does not carry out groups, no group shuffle split, and then also circle leakage not addressed because if they don't carry out the group shuffle split, then they have not addressed the shuffle leakage. Then why? Because they only operated on a single institution's data set. And then also, what is the result? Limited geographical generalization. So here for us, we study about 8 models to list but a few, and then we select the best model as per stability, whereby XGBoost managed to be the best model. And then our main challenge is the distributional shift across circles, where data of different circles are different, now giving challenges to our model to perform good on every given circle, because every circle that appears to it is new, but we handled that through group shuffle split, ensuring proper generalization. And then we are also having a limitation of single country, so not yet implemented. We haven't implemented federated learning. So the problem we have is that loan officers approve loans based on relation, not any data guiding them, not the ability of the person to pay the loan. They just put feelings and then grant the loans. And then identity and trust gap. What's the issue here? The issue is that loan officers, all these institutions, are unable to identify borrowers who have just defaulted somewhere and have just come in their circles to borrow again. Then blind spot, these loan officers just get shocked with defaulted loans, and then like just there before they know, the loan has entered in default state, checking the person has disappeared with the collateral. And then we also have computer challenges which are rotating around class imbalance, whereby if the model is not well trained, can achieve a high accuracy of about 75%, yet it is just gambling, surviving using the advantage of the baseline being 24.5 0.53%. Like this is the percentage of defaulters. So even if it just predicts everyone as non-defaulter, it will achieve 75% accuracy. Institutional leakage, whereby if the split is not done well, institutional leakage, let's say if it's just a simple data split is carried out, let's say uh, data from different one circle will go into train and test, and therefore model trains on that of that specific circle and then learns its pattern, then it faces it in test, scores highly on it, and then you drop this model on a new circle where it has not seen, then fails terribly. And then we handle that very well by making sure that we divide according to circles on no data from one circle goes into ends. So data quality prices, we have columns which are null, and then accounting inconsistencies, placeholder values on date of birth. Most people don't grant their date of birth. So our research question objectives. So the objectives we have are to carry out express data analysis, train, compare these models and select the best, deploy an API for usage, and then also establish the deployment framework, which takes in the shadow mode, assisted, and policy. And then in the questions that we have, we want to find out the borrower and loan structure and contextual features which carry the high predictive signals, and then which architecture is the best, and then also what are the repayment trajectory features that can reliably distinguish the stable, elevated, and critical loans. And then and then also to identify how can sharp-based experiment be structured to provide action and the regulation compliant adverse actions as required by the regulatory body of Uganda, that explanation be granted by every AI prediction made. So our contribution, we successfully carried out exploratory data analysis, unveiling new insights like overcollateralization paradox, whereby collaterals that are marked as excellent are the ones that even have high default rates, school fee seasonality effects. So shall look at them in exploratory. And then we also performed 8 model comparative evaluation under leakage hardened. So we did 8 model trainings. We evaluated them and then we compared them against each other under group shuffle split, and then basing on the stability we had to come out with the best model. And then also we carried out leakage auditing, and then we dropped those features that post disbursement features that are making the models to see in the the features that are not available during our application time. We dropped them and then ensure that every data passes through that pipeline of leakage auditing. And then we also deployed and also established an MVP of three-phase deployment. And then these are the methodologies that we go through. So we look at our, let's say, the data ingestion step, then we carry out exploratory data analysis, which gives us insight and decisions that we take to feature engineering. And then with feature engineering, then we come out with data sets that our models are able to learn on and make the best of. And then we carry out leakage auditing to ensure that our models are actually realistic or actually real accurate. And then we go on and we carry out model compression for performance purposes, like we distill the knowledge of the heavy model into a simpler model to ensure performance. And then model one, these are just the inputs of the model. So the borrower demographics, and then we have the collaterals, and then verification flags. There are about 75 features, and then the sense we are going to look at it in the next. So to clarify that in module 2 architecture is fully specified, but its training and the evaluation are deferred for the companion publication coming yet. And then we look at the looking at our pipeline. First, I start with it. Starting with our pipeline first, where I said we shall look at it, we look at raw input first, and then the next step is median input, where we fill in the missing values using the median, and then for numerical columns, and then we also categorical, so we scale the data, using robust scaler, which uses the concepts of interquartile range. Why are we using it? Because our EDA showed us that there are various outliers, and then we carry out one hot encoding. What is its purpose? The one hot encoding, we create binary column for categorical data or categorical columns. And then XGBoost, this is the brain of our loan application gatekeeper, like the brain of our model. All the logic that it uses to predict sits here, and then it carries out the predictions. And then we say that XGBoost is so we are going ahead to look at the architecture and mathematical foundation of each and every model. So we look at XGBoost being built one tree after another, where each tree acts as a refiner for the predictions made by the previous tree. And then this is the mathematical foundation, whereby we have the the objective function. The objective function being the goal of the model, but it's that the model is not only aiming at being accurate, but also it's aiming at being efficient. So that's why the regulator comes in, whereby it penalizes for every tree that is being created using the lambda function. The lambda and the gamma. And then we have since this model is built incrementally, one tree after another, so we have the construction function, whereby this is the current prediction, which is built up of previous predictions, and then we have the current prediction from the current tree that is scaled by the learning rate to ensure that the model learns slowly but robustically, not just concentrating on noise from one given tree. And then we handle our imbalance through scale pose weight. That's how we handle our class imbalance, whereby, so what is the 3.26 meaning for us? So this is only carried out on the train split, whereby the train had, these are the non-defaulters and these are the defaulters. And then 3.26 is meaning that when the model misclassifies a default, it should penalize it 3 times higher than when it has misclassified a non-default. So to progress further, just a quick wrap up over these other modules. We'll talk about logistic regression. This is this one. For it carries out, let's say, logistic regression. What logistic regression does is, for every feature that is existing, it generates a score for it, and then increments, sums up those scores. Like we have the weight here, and then we have the bias, and then when it sums up the scores, and then it squashes it into a probability using this function here, and whereby E is just the exponential that keeps the the value is between 0 to 1. And then we have how does this model learn? This model learns by just ensuring that it minimizes the loss entropy. That is logistic regression. And then random forest, this is just a committee of various trees, whereby the final output is the average of the prediction of all the existing trees. This function is indicating for us that this P here is the prediction from tree I for a given borrower X, and then we sum it up to the number of trees and then divide by the number of trees, giving us the average prediction. And then that boost uses ordered boosting, whereby and also ordered target encoding, whereby for it will just focus, it looks at the records coming in a given chronological order, in that what it is predicting currently does not exist at the moment. So it doesn't use what it is predicting to encode. So that's where it is beats other modules. And then we have, due to time, I will just kind of wrap up a little bit fast. So we are having we are having cabinet, sequential sparse attention. So this one applies the concept of sparse masks to select relevant features for a given borrower. So we are like this model for it. It doesn't, let me say, carry out the prediction on the entire feature set, but for each and every decision point, it selects a given particular what set of features in which to based on to make the decision at that point. So whereby so for time purposes, I will progress to discuss for us our data description and exploratory data analysis phase, whereby we had about 1,995 train eligible records that are filtered from 20,000 that are derived from over 46 circles from 15 districts, and then they have 75 variables, and these are the things that our exploratory data analysis phase reveals for us. So we identify class imbalance. That's where we identify that we need now to carry out class pose weight on XG boost and stuff like that. And then duration default. So however much it is not that monotonic, you can see, but it indicates for us a high correlation. If we zoom here, we have a high correlation between between default rate and the duration of the loan. So we derive insights from there. And then we have school fees seasonal effect, whereby we can look at the loan counts increasing in January and February when students are actually going back to school. And also similarly, the default rate increase like that. Also, you look at it in also October and November, it is the same thing. So and then we mark a month that is it a school fees month, and when we look at our sharp values, it carries a high predictive value. And then when we come here to our output results and discussions, so after training all those 8 modules, evaluating them and comparing them against each other, so this is the score in under validation and test. So so we can, when we focus on let's say XG boost and test leaderboard, because this is for circle disjoint split. Why did we carry out circle disjoint split? We said that we want to ensure that no data from one circle crosses to training and test, because that will make the model cheat just by identifying a pattern of a given circle. So for a single split, this is the results that we get. And then so we have here Briar score, which is showing us the Briar score is showing us how good a model predicts a given probability. How is the model good in predicting what the probabilities? And then and that's what our Briar score is indicating for us. And then we also have area under precision recall. So what area under precision recall is showing us is giving us that so we have threshold. So so we are like we are like F2 score is dependent on the threshold, but now area under precision recall is more independent. Why? We are looking at what if we just change our decision, we change the threshold, how well does the model perform? So now, and so these values, let's look at the value of 0.63, and then the value of 0.63 here, what is it indicating for us? It's indicating for us that given this baseline of the test data, which has a default rate of 30%, given that particular baseline there, our model performs 2 times better than just a random model that is gambling. So we are trying to say that that even if we change the threshold, increase or decrease the threshold, our model by around 60% will predict the what? the borrowers as defaulters or non-defaulters right. Its prediction will be right. So how is this area under precision recall derived? It is derived in a manner that we calculate, let's say we calculate the precision and recall under different thresholds, and then afterwards we get we plot, and then after plotting, and then we get the area under it, and then we have the F2 score. That one is the one that weighs recall more than precision. So then something else to note from from this test, you can look at the random forest being having a high score, let's say more than XG boost, but we say that XG boost was selected due to its stability across different circles, that it is more stable, its performance is more stable based on different circles that it faces. So this is the cross-cooperative stability analysis, whereby we are looking at the standard deviation like across 6 seeds. So across 6 seeds, what is the divergence? How does its prediction vary? So that gives us the insight that this model is able to generalize well. The one with the least standard deviation is the model that is not over diverging depending on different circles that it lands on. So it attains a good generalization, and that is XG boost for now. So we progress to looking at explainability. We are required to explain every kind of decision that our model makes. So we implement sharp predictive explanations that is grounded on the game theory, whereby every participant in the game makes a contributions, like the score of the participants is the contribution towards the prediction. So we use a kernel explainer with link entity, and then we use a background data of 200 data sets, 200 samples of the data sets stratified across different circles, and then we produce different artifacts to give us what our explainability has been able to achieve. So we have here the this is the bar graph showing us the average impact of every feature across all the tests that we carried out, because we carried out tests on 500 rows records for the tests. So this is the impact. So we are looking at a loan duration days having the highest impact, and then borrower loan count. So then we look at the B swarm here, whereby this one is showing us the impact that a given feature is having on every prediction. So the red shows that is the negative impact that the feature is having on that particular prediction. Every piece of dot there is a prediction. And then this one now we give an insight into why a given a high risk loan was rejected. So this is how showing us how the features are contributing. The blue ones is like the feature adds positively to the prediction, and then the red one, the feature deducts. That's why granted loans are full of blues only. So so you look at it, loan duration, days adds positively to this loan, and the rest of the features are adding positively. So that is for sharp predictive explanation. So then we look at our model selection and deployment. We said we base on group shuffle split for the 6 seeds, and then we look at the stability according to the mean and the standard deviation, and we had to select XGBoost as our best model. And then after selecting XGBoost, when we deployed it, looked at performance issues, and then we had to carry out knowledge distillation, which we are going to look ahead there. And then afterwards, then we deploy, and then we expose these endpoints, whereby this one is serving the interface as per now for the testing purposes, and then this is receiving the request to carry out the predictions. And then we also have a deployment plan whereby we have the phase 1 shadow, whereby it will run in parallel with the manual process. We don't change any decision. And then we also have the phase 2, whereby it is assisted. High risk applicant goes to the other side, and then it goes to the senior officers to verify it. And then we have our phase 3, which is the policy integration phase. When we look at the model compression, as I said, that we later, due to performance purposes, we need to make the predictions as fast as possible. So we have to develop a lightweight module. So how do we achieve that? We do model compression. Model compression is basically just squeezing a complex module into a simpler module, but without losing the logic or whatever the complex model has been able to learn. So what for us, the approach we employ here is knowledge distillation. And why did we choose knowledge distillation? Is because it preserves for us the complex nonlinear logic that XGBoost was able to learn. It's not all about just pruning the branches or eliminating some features. And then also provides a structural simplicity, why we are able to build a completely new module. And then through the dark knowledge transfer. The dark knowledge transfer is basically achieved through softening the teacher's predictions, whereby we apply the T greater than 1 to soften it, and then the relationship is revealed to the student, and then the student is able to acquire the knowledge from the teacher. So how do we do this? So we extract, this is the first, whereby it reveals the hidden relationship, and then strips the sigmoid compression to retrieve the teacher's raw decision. And then with the distillation happens here. Then if we, due to time purposes, we progress through the pipeline that we look at. So we have data loading and identical preprocessing. So through the process, we use the same kind of pipeline that was the data loading and processing pipeline that was used by the teacher module, so that the student is a mimic of exactly what the teacher is. And then we also establish the teacher's baseline, like what are we going to evaluate on, what are we going to base on, that we determine the basis of how much are we trading off for this lightweight module, for this improved performance, what are we trading off. And then after establishing the teacher's baseline, and then we generate the soft labels. So how do we generate the soft labels? We generate the soft labels by applying our T to those functions, as we demonstrated here, whereby we apply this T greater than I. We are like, when as long as we increase the value of the t, the distance between the predictions decreases. Let's say if we predict 0.9, we have 0.1 and 0.9. So when we divide that prediction by 2, so the difference between those two reduces. So the model can clearly see how this particular borrower resembles a defaulter, not just only a fine borrower. So and then we carry out loss blending, whereby we are stopping now the student model from just learning, let's say from just cramming only from the teacher. So let's say now if we use an alpha of 0.7, that means we are just trying to tell the student model that what you do is get 70% of your knowledge or learn from the teacher, and then what you do next is 30% you should learn it from the actual ground truth. So and then after the phase of loss blending, we carry out student training, and then the evaluation and of course. So this is what we base on to train the student, and then we do the evaluation and then the selection. And so this is the full comparison of the different student models we have been able to train. We establish their own baselines, given they are not students. The baselines learn from the hard labels, the zeros and ones, and then the students will learn from the soft labels from coming from the teacher. And then that's the comparison. And then here we look at the gains that all these models that we train are having, and then the one with the most gain comes out as the best model. So, so here, basically, we are looking at comeback decision tree has the best gain. It only loses on the Briar score, which is reasonable. But then on the rest, it gains recall of 0.43. And then it also gains area under precision recall of 0.059. And then we are looking at our model having a performance breakthrough, whereby, yeah, traditionally we expect the model to be slightly lesser than the student model to be slightly lesser than the teacher module. But for this case, it is a case which is well documented in scenarios whereby there is a label smoothing and the knowledge distillation as a regularization. So why are we saying that there is a gain? Because when we look at the students' F2 score and the teacher's F2 score, we look at the performance retention, which is 121%. And then how do we justify this? So it's not leakage or what, but we are having knowledge distillation acting as a regularization here. So whereby the the model, we architecture it to just have a simple structure, not a very complicated like the one of XGBoost, about 600 trees. Let's say if we look at this decision tree baseline, the decision tree baseline performs terribly. Why? Because it is learning basically from the hard labels. It's learning basically from the hard labels, and going having large number of trees, creating jagged kind of rules, which is not helping it to what to predict. And then the regularization comes in, whereby now this model has very few number of trees because it is already learning from from the hard work done by the teacher. The teacher already establishes the difference, the boundaries between the predictions, and therefore this model is able to learn from it. And then we have label smoothing effect, whereby we label smoothing effect, whereby we reveal the hidden relationship between the features to this student model, and therefore, so the model is able to learn through a smooth curve, and hence achieving high score. So So label smoothing, removing those kind of noise. And that's how our high score comes in. So then we have, this is our interface, how it looks like. Then this is the link to the model that is deployed. Um, so the officer just enters and then afterwards gets their predictions and also gets an explanation for why the predictions is saying whatever it's saying. And then we have some sort of limitations in our limitations, data quality issues, whereby we have columns which are null and then placeholder values, accounting inconsistencies. So, and then we also have geographical institution focus, whereby if the model is being deployed in a geographically different or different economic jurisdictions, the model may really perform slightly different. However much we have tried to put their cross-circle robustness, but these factors still impact a lot. And then class imbalance, presenting computational challenges. And then also we have not included the macroeconomic features such as inflation, central bank rates. Those are the limitations that we have. So, and then we go to our, let's say we look at our conclusions and then the future works, which shall be looking at more data collection and then shall be looking at formal fairness, addressing lending bias, and then we are also going to be looking at federated learning, whereby we are we are going to try to improve data sharing privacy, uh, preserving distributed protocol. So while we are trying to train on a given circle, data coming from a single circle is what we are looking at. And then we're also looking at providing USSD interface for officers who are unable to access internet. Yeah, these are the references for the work. Yeah, and we attribute the work to our supervisors and then our partners who were able to provide us with data. Thanks for listening.